So before I dive into the metric, I just want to say a few words about the structure of the space-time that we're going to look at. And in particular, one can think about the idea of horizons. Now, distances are actually horrifically complicated in cosmology. And that is because if you think about a distance, you think, well, the universe is expanding, that distance is changing all the time. And if I think about a distance I measure, how do I measure it? Do I do it by rulers, end over end, at the present moment? Do I do it by the light travel time? Because, of course, the light has been emitted when the galaxy was closer to me than it is now. Do I do it by some average? So distances are very complicated. So the first thing I'll note is that we can look at different forms of horizons and we can look at different forms of distances. And so for the distances, the two common ones that you'll see are the so-called proper distance. That's what goes into Hubble's law. And it's basically the ruler distance. And actually, perhaps more commonly, you will see a co-moving distance. A co-moving distance says the following. Suppose I have some little grid here. And I put galaxies at different points, and I have here x equals 1, 2, 3. And then at some future time, I make that bigger. X is equal to 1, 2, and 3. And so what I could say is that my actual distance, my physical d, is equal to some scale factor, which might just be a factor of time, times the actual distance that I measure here. And so this thing is the scale factor. And sometimes you'll see it written as r. And sometimes you'll see it written as a, and occasionally even as something else. I'll tend to use a here in this particular course because I think that makes life simpler because you don't get it confused with the Ricci scalar and the Ricci tensor and the Riemann tensor and all of that. Although sometimes r is a little bit more intuitive, so we'll use r when we derive the metric because it is a physical distance and a can be a bit confusing. But hopefully it will become clear as I go through. So having got distances, you can then think about horizons. And so the simple horizon is the Hubble horizon. And that simply says if TH is equal to 1 over h naught, then DH is just equal to C over h naught is equal to C times the Hubble constant. So that is the light travel time in the age of the universe. And you might think that would be the real physical horizon, but remember, space-time itself is expanding. The expansion of the universe is different from Doppler shifts of things moving through space-time. Space-time itself is expanding. And so there's another concept, which is the real causality statement, which is called the particle horizon, and that's the causality barrier in the past. And so you can think about, a photon or a null geodesic it's the most distant object you could see. And then there's an equivalent of the particle horizon, and that's the event horizon. And you can think of that as being a causality barrier in the future. I.e., if you send a photon out now, what is the most distant object it can ever reach. And you'll notice that this first horizon is very simple to calculate, because it just depends on the age of the universe. The particle horizon and the event horizon are more complicated because they depend on the expansion history of the universe. That's the expansion history and future of the universe. If the universe is slowing down, comes to a standstill and starts collapsing back, your light ray can find potentially more distant co-moving coordinates or even proper distances than if you can't otherwise. You know, if it expands forever at an accelerating rate, for example, it's different. So your particle horizon and your event horizon depend on the expansion history and the future of the universe, and we parameterize that all through the scale factor. So for example, A0, the scale factor today, equals 1. And it's smaller in the past and bigger in the future, as long as the universe keeps expanding. And so what does that space-time actually look like? Well, I'll try and draw it now a little bit. You know, if you've got the now, you've got us, and you've got these, and you've got your sort of classic light cones around us at this moment. See how well I can draw that it thinks my circles are in fact, or my ellipses are in fact squares. Let's try that again. So, you've got your light cones here. If I draw you're really doing well here. Let's try that one again. Better, okay. So this is now. This is your event horizon. Okay, so it's currently space-like separated, but in principle, of course, in the future, it crosses your light cone. This back here is your particle horizon. And so, you know, regions in here are time-like. Regions out here are space-like. So regions, you know, currently outside your light cone are potentially reachable in the future. And this is roughly what the space-time that you're dealing with looks like. But of course, all of this is taking place in a space-time which is also expanding or contracting. So the size, if you like, that you can, you know, not the light cone, but of the physical things you can see, is varying in the future. And you need to think about the definitions of distance and the definitions of time in quite complex ways that I'm not going to go into to really delve down deeper into that.